Okay, Unit 5 is covalent bonding. Remember that covalent bonds share electrons and they're between nonmetals. That you should know from our previous unit. You should also know that ionic is metal and nonmetal, and they transfer electrons. You also still need to remember the properties of ionic. And then you have metallic, which is a sea of electrons, and that it contains just metals. And you need to still remember the properties that go along with metallic. So we made a foldable in this unit to help us organize those properties. Given a set of data, you should also be able to pick out, using your properties in your foldable, what type of bonding that substance has. There's a special class of molecules called the diatomic molecules. Di means two, atomic refers to the atom. So these actually exist as two atoms together. So instead of finding just hydrogen atoms by themselves, we always find the hydrogen atoms paired together. So there's a couple ways of remembering your diatomics. You can remember Hofbrinkel, or you can remember the magic 7, where you would start at number 1, which is hydrogen, go to element 7, which is nitrogen, and then draw a 7 with your finger: oxygen, fluorine, chlorine, bromine, and iodine. So all 7 of these molecules exist as pairs of atoms instead of single atoms by themselves. They also all have non-polar covalent bonding, which means that within our H2, the atoms are sharing their electrons equally. Number of bonds. When you have two nonmetals coming together, you can actually form more than one bond between the two atoms. A single bond, you have one bond, which means you're sharing 2 electrons. And that's like in our hydrogen. Hydrogen has 1 electron. It wants 2, so it forms a single bond within itself. A double bond means that you have 2 bonds. In other words, you're sharing 4 electrons. Oxygen, which has 6 valence electrons and wants 8, will share and share to make a double bond. A triple bond, you have 3 bonds between the 2 atoms, which means you're actually sharing 6 electrons. And that's like our nitrogen. Nitrogen has 5 valence electrons, wants 8, so it will share, share, and then share. Bond length is simply the distance between the atoms, and bond energy is the energy needed to break the bond. So the more bonds you have between 2 atoms, the closer the bonds, or the closer the atoms become. So nitrogen with a triple bond has the shortest bond length, and hydrogen, which only has 1 single bond, has the longest. Bond energy is the energy needed to break the bond. So the more bonds, more connections you have between the 2 atoms, the harder it is going to be to separate those atoms. So nitrogen, with the shortest bond length, has the highest bond energy. The one with the longest bond length would then have the lowest bond energy because you have less connections between the 2 atoms. Electronegativity differences also tell us the type of bond. So if you were to subtract the electronegativity values, and that value falls between 0 and 0.3, then it's a nonpolar covalent bond. If when you subtract the difference, it falls between 0.3 and 1.7, then it's a polar covalent bond. And if it falls between 1.7 and 4, then it's ionic. These values must be given to you. This is not something that you're supposed to know. So they're actually on page 169 of your textbook. You subtract and you see where it falls in. So again, we're looking at page 169 to get these values. On page 169, it says that sulfur's electronegativity value is 2.58 and hydrogen's value is 2.20. Now we want to subtract to get a positive value, so you always take the big number minus the little number. And we get a value of 0.38. So 0.38 is greater than 0.3, so it would fall between 0.3 and 1.7. So this is a polar covalent bond. Here we have sulfur and chlorine. We already know that sulfur is 2.58, so on page 169, chlorine is 3.16. We want a positive number, so we're going to take the larger number, 3.16, minus the small number, and we get a difference of 0.58. So 0.58 would fall between 0.3 and 1.7, so this is polar covalent as well. Oxygen and chlorine. Again, we already know that chlorine is 3.16, so now we're going to look at oxygen. Oxygen is 3.44. We take the large value minus the small value, and we get 0.28. 0.28 falls between 0 and 0.3, so this is actually nonpolar covalent, and they would share their valence electrons equally. Number 4 is not a trick question. Hopefully you recognize this as a diatomic, and all diatomics are nonpolar covalent. So how does this work with electronegativity? You're actually subtracting it the same value twice. So bromine is 2.96, and we would say minus 2.96 because the bond is happening between two bromine atoms. So we'd actually get a value of 0. In number 5, we have cesium and sulfur. We already know sulfur is 2.58. Cesium is 0.79. So we take the large value minus the small value, and we get 1.79. Well, 1.79 falls between 1.7 and 4, so this is ionic. In number 6, even though we have this subscript 2, our bond is still happening between a calcium atom and a chlorine atom, so the 2 does not play a role at all. We're just looking at calcium and chlorine. We already know that chlorine has an electronegativity value of 3.16, so calcium is 1. So 3.16 minus 1 would give us 2.16. That falls between 1.7 and 4, so this is also ionic. C and O. Carbon has an electronegativity value of 2.55, so we would take oxygen, 3.44, minus carbon, 2.55, and we would get 0.89. 0.89 falls between 0.3 and 1.7, so this is polar covalent. Finally, we have magnesium and oxygen. Magnesium is 1.31. Oxygen minus magnesium, remember big minus little, would give us 2.13, which means this is also ionic. Now if we just look at our polar molecules, which one is more polar? The more polar molecule is going to have the greater difference. So that would mean CO is the most polar because it has the greatest difference. If we look at C and O, which one would be controlling the electrons more would be the one with the higher electronegativity value. So oxygen would actually have the electrons more often than carbon because its electronegativity value is larger. If we look at S and Cl, Cl would have the electrons more often than sulfur because it has the larger electronegativity value. And then S and H, S would have the electrons more often because it has a larger electronegativity value. A Lewis structure helps us determine what the shape of the molecule is. So it also determines the polarity of the molecule. To figure out how our atom is structured and if there is a double bond or a single bond or a triple bond, we use the formula Watt minus half divided by 2 to tell us how many bonds we have. This is not something in your reference table, it's something that you have to remember. So for example, you have NH3. So you have N and you have 3 H's. The want is the octet rule. Everybody wants 8 except for hydrogen who wants 2. So 8 plus 2 plus 2 plus 2 gives us 14. The half is the number of valence electrons. Nitrogen in group 15 has 5, and hydrogen in group 1 has 1. So then you take your want, 14, minus your half, and you get 6. Divided by 2 tells us that there are 3 bonds. The first element goes in the middle unless it's hydrogen, then it's the other element. So we're going to put nitrogen in the middle, and we're going to surround nitrogen with 3 hydrogens. Then we're going to bond our nitrogen to our hydrogen. I've drawn 3 lines, which represents my 3 bonds. That tells me this molecule does not have double or triple bonds. However, I want to make sure that my atoms have what they want. Hydrogen wants 2 electrons, and it has access to 2 electrons because of the bond. 1 bond, 2 electrons. So all of my hydrogens are satisfied because they have access to what they want. My nitrogen wants 8 valence electrons. Right now it has access to 2, 4, 6. That means it has 2 electrons that it's not sharing with hydrogen. So we just draw 2 dots. Those 2 dots are called the lone pair. It's called a lone pair because it only belongs to nitrogen alone. Alright, if we look at SO2 for something a little bit more complicated, we have sulfur, oxygen, and oxygen. So want is the octet rule, and everybody wants 8 except hydrogen. So that gives us a total of 24. How much do they have as their valence electrons? So they're both in group 16, so they both have 6 valence electrons for a total of 18. So then we would say 24 minus 18 is 6, divided by 2 is 3. So I know that I have 3 bonds. The first element goes in the middle, unless it's hydrogen, and then we have our 2 oxygen atoms around sulfur, and we bond them to sulfur. Now I've only drawn 2 lines to represent 2 bonds, but I calculated 3. Because my bonds don't match what I calculated, I know that there has to be a double bond. So that third bond is going to be a double bond. It doesn't matter which oxygen you double bond because they're the same, so I'm going to do this one. So now I have my 3 lines drawn to match my 3 calculated. Since everybody wants 8, I know how many dots to add. My oxygen down here only has access to 2 electrons, so that means it's not sharing 6 electrons. This oxygen has access to 4 electrons coming from the double bond, so that means it's not sharing 4 electrons. The sulfur has access to 3 different bonds, so that's 6 electrons. That means it's not sharing 2 electrons. CF4. You have carbon and then 4 fluorines. The want They all want 8. That's a total of 40. Then you have carbon has 4 because it's in group 14. Fluorine has 7 because it's in group 17. And that's a total of 32. 40 minus 32 is 8, divided by 2 is 4. So I have 4 bonds. The first element goes in the middle, unless it's hydrogen. And we have our 4 fluorines going around the carbon, and we bond them to carbon. I've drawn 1, 2, 3, 4 lines that matches my 4 bonds calculated, so I don't have a double or a triple bond. I want everybody to have 8. Carbon has access to 4 bonds, which is 8 electrons. So carbon is happy and I don't need to add any dots. Fluorine wants 8 and it only has access to 2 electrons from the single bond. So that means it has 6 electrons that it's not sharing. Fluorine has access to 2 electrons, so there are 8 electrons it is not sharing. Fluorine has access to 2 electrons, so there are 8 electrons that it's not sharing. And then the same with this fluorine. OF2. You have oxygen and 2 fluorines. They all want 8 except hydrogen. So that gives us a total of 24. Oxygen has 6 because it's in group 16. And then fluorine has 7 because it's in group 17. So that's a total of 20. So we'll do 24 minus 20, which is 4, divided by 2, which is 2. Oxygen would go in the middle. We have 2 fluorines. We bond them to oxygen. We've drawn 2 lines to represent our 2 bonds. Then we have to make sure everybody has what they want. Fluorine wants 8. It has access to 2 from the bond. So it has 6 that it's not sharing. Fluorine has access to 2 from the bond, so it has 6 that it's not sharing. Oxygen has access to 4 because of the 2 bonds, so it has 4 that it's not sharing. A polar molecule is when you have a lone pair on the center or you're not symmetrical. So if we go back, here we have the lone pair on the center atom nitrogen. That means that this is a polar covalent molecule. Sulfur, being the center atom, has a lone pair. That means that this is a polar covalent molecule. Carbon does not have any dots and it's symmetrical, all fluorines. So this is a non-polar covalent molecule. Oxygen has 2 sets of lone pairs, so this is a polar covalent molecule. And this one, because it has the 2 lone pairs, is actually more polar than our other 2 molecules with the 1 lone pair. Resonance just means you can draw more than one Lewis structure and be correct. So here we have carbon and 3 oxygens. So 8 plus 8 plus 8 plus 8 is 32. Half. Carbon has 4 from its valence electrons. It's in group 14. Oxygen has 6, so that's a total of 22. Now you have this -2 charge. Negative means you've gained 2 electrons. So that means we actually have 2 extra electrons for a total of 24. 32 minus 24 is 8, divided by 2 gives us 4 bonds. So carbon would go in the middle, and we have 3 oxygens to bond together. 1, 2, 3. I've drawn 3 lines, but I have 4 bonds that I calculated. That means that there is a double bond somewhere. Oxygen wants 8. It has access to 4 from the double bond, so that means there's 4 electrons not being shared. Carbon wants 8, and it has 4 bonds, which gives it its 8 electrons. Oxygen wants 8, but it only has access to 2. So that means it has 6 electrons that it's not sharing. Same with this one down here. Now the resonance happens because the double bond doesn't have to be on the first oxygen. It could have been on the oxygen on the other side. Or it could have been on the oxygen on the bottom. So that's resonance. Also notice that carbon does not have any lone pairs on it, so that means that this is a non-polar covalent molecule.